Good morning, everybody. Welcome to this webinar by ETIP SNET, and in particular by the working group 1 of ETIP SNET on the topic of sector coupling. This is one of the series of webinars. The next one will be on June 30, and it will be on a similar topic. Welcome to this virtual room. Of course, in this period, we cannot do as we had wanted to do a physical meeting with more interaction. My name is Antonio Liceto. I work for the Italian transmission system operator, Terna, and I am co-chairing this working group. I was actively involved in this work. Today we are going to see 1 hour and a half, hoping that the technology will help us. I'm trying to go to the next slide with the remote control. I want to show you the agenda and the speakers. We tried this before, but now it seems okay, just a question of a little delay. Sector coupling is the topic of many conferences and actually many initiatives also at the political legislative level in European Union. What we would like to give you here is an overview of concepts, definitions, and description of state-of-the-art for power-to-X technologies and development potentials. The agenda of today is Janoko Ziegler, the chairman of Working Group 1, will give a short presentation of ETIP SNET and what we do for those who are outside of this European platform for research and innovation. And then we mentioned that all what we discussed today is a part of a white paper which has recently been published. We will give you the link. Then we will touch upon some concepts and framing of sector coupling, and then we go to the technological parts: power to gas, power to heat, power to mobility. And then conclusion, then most important, we dedicate some time to answering the question from the audience. So at this point, I will give the floor to Janoko. Gustavo, please can make him the speaker.
Okay, you should be able to speak. Yep.
Yes, good morning, everyone. So welcome to this first of a kind webinar due to progressive digitalization and some emergency, but we always take advantages of this situation to evolve, right? So I'm glad to have you all here connected, although as Antonio rightly said, it would be nicer to have you to see some of you at least. I'm Janoko Ziegler, so I'm born German, but I nationalized Italian as well, and I'm working in NL for 20 years now. I'm into global infrastructure and networks, market studies, and since a few months now, currently chair of this working group 1. Okay, let's see if it works to swap slides. I'll just give a brief introduction and keep it short, but as Antonio also said, some of you are external and it would be nice to get an overview. As you see here, what this energy transition and implementation plan, which is what ETIP means, is all about, is to give this integrated view and approach involving all stakeholders. And that's why we'll see that there is members within these specific working groups, working group 1 dealing in particular with smart grids of the electricity network, that involves hence all these actors from across the value chain. You see here all these little icons, like obviously research and academia is involved, the consumers, the storage devices, the challenge to connect all the upcoming ever more renewables to the grids, digitalization, which means ICT, etc., equipment manufacturers, but also the interface to other energy carriers. And that's what we're going to talk mainly about today, the sector coupling. So the link of the area working group 1 covers in particular, which is electricity smart grids, to others, heat, transportation, gas, etc. So if we go to the next one. Exactly. So this is the backbone of our working group's work. It's basically we worked in the last years on the vision, where to go for 2050. This is evolving in parallel with the Commission's ideas, requests, and so we talk more and more about 2050 also in these targeting decarbonization, especially for Europe, by that the date at the latest. So the vision was published in 2018. It was followed by the implementation roadmap 2020 to 2030, so next decade. That was published recently in February, and it was followed by a more specific implementation plan on research and innovation initiatives on mid-May. You have here the links where you can download these publications. Now, go to the next one. Exactly. That's just a very short recap of why sector coupling is interesting, because this is like the heart of a system, electricity being one of these energy carriers that you just can't live without, as we are experiencing right now. I mean, we wouldn't be able to have this conversation if it weren't for electricity. And it's a linkage between gas networks, current, future gas users, liquid fuels, thermal networks, and as we listed here to your left, these known drivers for the energy transition, like Europe targeting global leadership in the renewables deployment by at least 2050, but possibly much earlier globally. Electrification, additional electricity users, e-mobility, become carbon neutral as fast as possible, sustainable also in the building sector, not only mobility, and all this thanks to widespread digitalization. So let's go to the next one. So what is this ETIP SNET organization about? We are 5 working groups and a national stakeholders coordination group. Currently, this webinar today is being held by Working Group 1, that's us, on smart grid, on the smart grid system specifically. But you see there's also other groups on storage, on flexible generation, on the customers and innovation. And we all respond to the ETIP SNET Secretariat and the governing board. There is a governance small schematic to your left, so that you can see that all these stakeholders cooperate to make sure we satisfy to some extent and bring as input the experts' knowledge and consultation regarding all these issues to the European Commission and further stakeholders. So here, next one. See if it works. Second, yes, here we go. So it's about efficient smart grid systems, right? We look at we have been looking at that for the last 4 to 5 years now, and it's progressive. As you see, we'll discuss today a first paper, white paper, the working group realized on sector coupling, but things evolve. We want to go more into detail as well, so we're currently actually already working on the second white paper. So it's really about how to optimize everything connected and that has to do with electricity grids, and with the integration of this electricity backbone architecture within the overall energy system. See if it works. If I want to change here, yes, coming. It's a bit slow. Okay, and this is just don't go into details, but it's just to show you that we are many, and most of all, we come from many backgrounds. So we are currently 32 people in Working Group 1. And as you see, there is 8 different stakeholder groups, right? Research, storage, as I mentioned before, ICT providers, DSOs like myself, distribution system operators, but also transmission system operators like Antonio. And then, so you see on the first pie chart on the top, you see those stakeholder groups represented. Research and academia accounts for almost half of us. So I would say it's really significant and very nice to have so many expert brains with us. And also in terms of geographical division, as you see below in the second pie chart, there's many countries represented. And so we cover basically all Europe, and that is nice to have as well. Quite an active group, so I'm very glad to be able to chair it and to be able today to introduce you to the presentation from my colleagues of this first work on sector coupling. But by the way, be mentioned here with the next slides. So it comes. We are obviously involved in international cooperation, so it goes into currently coordinating with the European Utilities Week, now called ENLIT. It was due to be held in Milan end of October, but it's going to be postponed to next year as for the physical part, while digitally there will be webinars starting from July all the way to end of November. There is partnerships like the 2.0 partnership on e-mobility, again coordinated by Antonio, very interesting. SIGRE, also our cooperation with SIGRE, and our cooperation with ISGA, with the International Smart Grid Association. That is an initiative that started in 2012 by the Clean Energy Ministerial, so it's a G20 initiative, and it's a bit rather more global than ETIP SNET, which by definition is of a European scope. Okay, with this, I would give the floor back to Antonio. Thank all of you and wish all of you a very instructive and useful discussion on sector coupling. Thank you.
Thank you, Occo. So these are the details of the white paper, which was published in January. You have the link here. And you can download it. It's public. All what is produced by ETIP SNET is by definition public. And about the second work, I should have the control now, Gustavo. Maybe it's only slow. Let me see if it works. We have a plan B, but we try to stick to this. Yes, the white paper is a bit wider than what we are going to present here. Of course, it's some tens of pages. So for more details, you can go to that one. The second work on white paper will be a bit different. It's not touching anymore on the technologies of energy conversion, but on many other issues around this and the ecosystem. So building blocks, interoperability, some digitalization aspects, and architectures, and also economic assessment of use cases. This will become published in the end of the year. So entering into the topic of today, we have to be a bit preemptive on the timing of this. There is some delay. About the today, because of the issues. So we are in the big paradigm shift that we are having today. We see that we are passing from a management of the network as load. The generation has to follow the load, which was typical and classic. It means load is an external independent variable, and the generation has to adjust to it with its flexibility. And we are now in a transition period where we talk about residual load, but we will arrive when the dominance of variable renewables will be paramount to a situation where the load will have to follow the generation. So we have to make flexibility into the load, into the grid. And so the flexibility has become the most important issue for grid operation. I think we will have to go to the plan B, Gustavo. If you can take the control, and I will ask you from this moment on to go. So flexibility is both in operation and in planning. When in operation, to how to best use and combine from a techno-economic point of view all the many flexibility means available. And planning takes a step further to plan in a coordinated way all this, not only the grid reinforcements, but also the load and the generation evolution and the flexibility means evolution. So we can categorize in many ways the flexibility. Here it is categorized by sector where they lay. We have, first of all, some flexibility, not so much into the grid, which is already being used at the maximum level. We have flexibility in generation, the traditional one. This is thermal plants or hydro plants, which can be adjusted with a certain time constants. But then now we need to have flexible loads, which we had traditionally with interruptible customers, which is a very rough way to call a flexible load. We will have demand response, which is a low-hanging fruit. It will be important. But then now they have become important. Other flexibility means, first of all, storage. Storage we can classify in many ways. Here again, classified if it is within the control of electric system or beyond. So whatever device is directly connected to the electric system and exchange energy in form of electricity and gives it back again in form of electricity, this is normally under the control, it is connected to the grid, so it is under the control of the electric operator. But then the next stage, and actually what we are dealing today, is to have flexibility. Here it is written storage, but it's not only storage, it's also more flexibility means in other energy system. So in the next slide, we can see that this can be different energy sectors. And typically the transport, the district and industrial heating and cooling, but also not only industrial, also residential through the district. It can be in the forms of molecules touching on the chemical industry, so producing hydrogen and all its chemical derivatives. You can have synthetic fuels, and eventually these molecules can also be transported. So there are many definitions we can give of sector coupling. Here what is given is still from an electric operator point of view, because this is also important to say that if you couple sectors, you have to match the needs of both or more. There can be more than two sectors which are coupled. Of course, we as ETIP SNET, in particular Working Group 1, we see the perspective from the electric system. This has to be matched with other perspectives. So sector coupling in general can be seen as an optimization among multi-energy option for supplying final uses. And on top of this, more advanced uses of interpretation of sector coupling is to have CO2-free fuels for transport, and even alternatives to power transport with molecular transport. Next one, thank you. And another way to consider the sector coupling features and possibilities is to see which system component, each system component, which characteristics can have and give to the wider energy system. So, for example, if here we categorize starting from the pure load, traditional, which is just a passive load, it can become going to the right of this table. You go to the, increase levels of sophistication. The pure load can become a flexible load with demand response and other means. And so this already gives a good means to the operation of the grid. Then we go to the storage in electric system or in other energy system, and even then to molecules. So if we classify them according to if they are end uses or only conversion, and in case the energy flow is reversible, these provide flexibility capabilities. In the next slide, we can write to this, which is one of the possible classification. So what is giving storage, flexibility, and energy carrier is the same table, but with colors which help to read, which are the most interesting categories here. So sector coupling is actually there when you are coupling the electricity with another sector, which is existing independently. What I mean is, if you have a storage device like a battery connected to the grid, this is there only for the grid. It has no other use. If you connect the battery of a car, this is there mainly for the transport and can give a service to the grid. So you are actually coupling the transport and the energy sector. Sometimes you find it power to X, which all of these terms are not synonyms. Power to X can include at least semantically the transformation in other mechanical or thermal energy. But if it is not a final use, I wouldn't call it a sector coupling. Next one, thank you. So I would like to show this graphic, very simple but systematic representation. First of all, we start from the left. It is green electricity, because all what you say is meaningful if we have and we want to decarbonize. And to decarbonize, first step is efficiency increase and electrification instead of using CO2 fossil sources. So whatever end uses you can electrify in a technical, economical, convenient way, this is the first option. If you cannot, then you can convert the electricity in other forms of energy. If this is green electricity, and the converted energy can be fed to the end users, and again here we have decarbonize. It is important to always, when we consider a project or an initiative in sector coupling, first of all to ask ourselves what is the main goal, maybe more than one. In these two cases, on the left side, the main goal is decarbonization. Once the energy is converted, you may storage in other forms, typically thermal or chemical, and in that case you can either use it as such, or just store it and convert it back. So you shift in time, and if you can even transport it, you shift also in space. And these are flexibility means to the energy system, but you lose the losses in conversion. Well, the color of the arrows here is going from dark green, which is the most convenient for the system, to the red and dark red if you convert back even to electricity. Of course, this can be important for some backup emergency, but is the worst from the efficiency point of view, because you have multiple conversion. We can go in the next one. It's important to say that either the goal is decarbonization, or it can be optimization of the infrastructures, either in operational or in planning stage. I see this as the two main categories to go for sector coupling projects. They may coexist, but it is important to have them in mind, because then when we have to assess economically any project in an agnostic way, so not coming from a pre-conceived idea that, for example, we have to go for hydrogen because everybody is going to hydrogen. I think the concept, the right concept should be, what is the goal for this project? Let's build the use case, and then we put the numbers, economics, it becomes a business case, then we can assess it. So it's always important to assess this project in versus the best alternative that we have without sector coupling, but achieving the same goal. I would go to the next one. I hurry up. The slide will be available, so if you want to deepen on that, but we have to respect the timings also for the overall presentation. Here you can see a taxonomy. It's about a trend now to make some taxonomies. If the rationale of a device or an equipment is an end use, or it is more for storage. If it is pure storage, it is doing only this, giving flexibility to the system. If it is only for end use, is the traditional loads, maybe with some flexibility. If we combine an end use on another sector with storage and flexibility, then we come to the dominion typical of sector coupling or power to X. I have put in this figure electrification a bit on the side, because electrification per se, as it is not giving flexibility. So it's not to be considered as sector coupled unless, as it is actually often the case, it is done in a smart way. For example, if I go to electric cars with non-smart charging, I just have an extra load in the grid, in the system. I need to make adequacy adjustment to the generation fleet, to the grid, especially distribution grid. So I have an extra stress to the system. I don't have help. If instead I use smart charging, then I have another flexibility means, because I can control from outside the rate and the time of charge, and this gives flexibility to the system. Next one, thank you. And another form of taxonomy can be based on the flexibility features. You can ask yourself, since flexibility is the paramount need of the grid of the future, according to if they can give or not and how much flexibility, you can have a taxonomy based on this. I think next one, I will give the floor. Let's check. Yes, I give the floor to Marie Münster, who was leading author of the white paper. Please.
Thank you, Antonio. I'll just try to see if I can change. Do I have the controls? Well, then maybe Gustavo, next slide. Yes. So just overall summarizing the white paper, looked into all the different types of technologies that can be applied to achieve this sector coupling that Antonio just gave us the outline of. So we looked into storages, not so much, but quite a lot into power, heating and cooling, which my colleague will tell you about shortly, about power to mobility, which Goran Strbac will tell you about from Imperial. And then I will talk about this power to gas and fuels. So this work was a cooperation between colleagues from the Technical University of Denmark, Imperial College, University of Liège, and also ABB, and then of course ETIP SNET, represented by some of us, and also Antonio. So next slide, please. The reason why we want to have this power to gas is that electrolysis can help us decarbonize and also store energy. So we can have electrolysis producing hydrogen either for direct use for transport or peak power and heat. We can have hydrogen that we use to produce, for example, ammonia, which we can use as fuels for shipping or fertilizers. And we can also use hydrogen in synthesis with carbons in order to produce chemicals or different fuels. So as a result of the production of electrolysis, we may have oxygen or heat that we can utilize for other means. Next, please. And if we focus on the electrolysis, you can see that electrolysis can be used to produce power to gas, just as hydrogen. It can be used in methanation to produce methane or CH4. And then to the left, you can see we can use it to produce a variety of liquids. And these different gases and fuels feed into the transport sector, the industry. We can feed directly into the grid, and then we can feed back to produce electricity in peaks, and we can use it in the residential and commercial sector. And we may get excess heat from several of these different processes. Next, please. If we start by talking about electrolysis, we can talk about 3 different types that are the main types. We have alkaline to the left, we have proton exchange membranes on the middle, and we have solid oxide electrolysis to the right. And you can see that the costs of the solid oxide electrolysis is currently higher than the others. But if you look to the right, you can see that where we are at more or less with the efficiencies, and you can see that the efficiencies of the alkaline and the PEM are comparable, whereas the solid oxide have higher efficiencies, and this is why we might accept the higher costs. Next, please. So on the maturity level, there is also a difference. So we have a high TRL for so a technology readiness level of the alkaline, a bit lower of the PEM cells, and the solid oxide is more a demonstration level or TRL 6. And then that also matches the deployment scales, where we are deploying at megawatt scales for the 2 first types, whereas for solid oxide, we're more at a kilowatt scale and trying to scale up at the moment. Next, please. If we talk about methanation, I'm sorry that the head titles have disappeared. They were there when I made the slides. But when we talk about methanation, we're talking about producing methane or CH4 from biogas or CO2 and adding hydrogen into the mix. We have 2 different main types. We have catalytic and biological methanation, where catalytic methanation is an exothermic thermochemical process where we operate at high temperatures and at high pressures. It's currently deployed at megawatt scale, so it has a TRL around 8, with the hydrogen to methane conversion efficiencies up about 77%. And if we talk about the biological, these are microorganisms that act as catalysts, and these are under anaerobic and aqueous conditions, and moderate temperatures and low pressures. So in the future, we might expect this could be a low-cost option. This is an emerging technology, so we are more at a TRL around 6, and we're currently deploying it like at kilowatt scale, expecting to reach methane conversion efficiencies of 80%. The projected costs are between 75 and 1,000 euro per kilowatt, so it's really a large span, and it's really a developing technology. But we have more than 30 catalytic or biological power to methane pilot projects being planned or already in operation. So it's something that we see coming. And I can say that in Denmark, I think we had around 20% of the gas in the grid last year being from biomethane. So there is a potential for converting from natural gas to biomethane in these ways. Next, please. Then going to electrofuels, so these liquid fuels where we add hydrogen. To the left, we have Fischer-Tropsch, we have methanol, and we have ammonia processes. We see that we are still kind of developing the ammonia, but we are expecting large decreases in costs on the Fischer-Tropsch and the methanol. And for the ammonia, we're expecting kind of levels at the level we are today with the capex for the others. And on the OPEX, on the other hand, we expect lower from the ammonia plants. And in terms of efficiency, then we expect a higher efficiency. And as I mentioned, ammonia, of course, used as fertilizer, but could be used for shipping as well. Next, please. In general, for all of these processes, it is established technologies, but they're not really kind of implemented in large scale for power to liquid processes. There are some examples. So for Fischer-Tropsch, there are examples in Dresden and in Norway, for the methanol in Iceland. And then for ammonia, there are also some examples, albeit maybe at a smaller scale. Please move on. If we talk about the potentials for power to gas or power to X in general, here are some examples of studies that have been made, where we see at an EU level a study saying that if we have 63% variable renewable energy supply in the electricity sector, it would be feasible with around 58 gigawatts of electrolysis, an additional 9 gigawatt of methanation, and another study with a 95% reduction in greenhouse, back please, 95% reduction of greenhouse gas levels in the EU, reaching around 260 terawatt hour of synthetic methane. And in Northeast Asia, they're expecting up to around 720 terawatt hours of synthetic methane. So we do see potentials in different studies for this technology. Next. This is now an example from a German study where we see that around the Ruhr district there is quite a potential going forward, and the total hydrogen demand in that study is estimated at 94 terawatt hours for the whole of Germany in 2030. Next, please. Yes, and this is now illustration of which countries have recently made hydrogen strategies. We've seen hydrogen strategies in Portugal and in the Netherlands and in Germany and Norway. And we are planning to make one in Denmark, and at the EU level, there's also plans of making one. So, and also in Australia, New Zealand, and South Korea. So this is really something that is moving, and where the governments have a lot of focus. And I think it's also really part of the focus now that we have this green transition, where we need to reinvest in order to come over the current pandemic. There's a lot of focus on investments in power to X as well. Yes, I think that, so if I summarize, it has a promising future. It can be an enabler for sector coupling. It can provide flexibility. It contributes to the greening of the difficult sectors, industry and transport, and it can boost the limited available resources of sustainable carbon and biomass. So in general, we can say that barriers to having this implemented at large scale are both in terms of technical, where we still need some development, and then economic and institutional and regulatory considerations, where we need to facilitate these technologies and the integration of markets. And I think that concludes my presentation. Thank you.
Thank you. I will take over here from Marie. I will explain a bit about the power to heating and cooling. So yes, please, next slide. So there are various different uses for power to heating and cooling, and today I'll go into detail with the district heating part, but just to give you a brief summary, we have potentials in residential buildings. Typically, you can see heat pumps in residential houses. Same thing for power to heat in industry, where you perhaps see slightly higher temperature demands. for district heating as well, which we're going to discuss today, and then of course power to cooling, which is another field that you can read more about in the study that we've done. Next slide, please. So with this example, I'm taking point of departure in power to heat in district heating. Many of the principles I'm going to discuss applies in the other sectors that I just described. But essentially, if we start out in the top right corner, we can see this chart with the heat production cost as a function of the electricity price. So heat is on the vertical axis and electricity price is on the horizontal axis. You have two production units. One is the power to heat. Another is, for instance, a boiler. You can have many different setups, but in this example, we're just taking point of departure in a boiler. And those are operated according to generating the least cost heat so the optimization is according to heat demand. In this case, if we look below the chart, we can see situation 1, and we can perceive it either as dispatch according to carbon footprint in the grid or amount of renewables, or if we look below in the figure, you can see that the price in situation 1 is very low per megawatt hour of electricity. So in the first case, we have a lot of wind in this case in the system, which is satisfying the electricity demand, but maybe in addition being consumed to generate power to heat in electric boilers, heat pumps, those technologies. Then optionally also having a thermal storage. You can see that at the bottom of the chart, where you are enabling a shifting in time by a very low cost storage option of your thermal demand. In the second situation, you may have higher cost electricity, or you may have lower amounts of renewables on the grid, and in that case, it may make sense to operate your system based on the heat storage, for instance, or a boiler. And that is situation 2 on the chart that you can see. So I hope this illustrates the fundamental concept of how you can dispatch your system and make it flexible and coupled according to the combination between heat and electricity. So essentially what I'm saying here is that when you have low prices and high renewables, you can dispatch your power to heat, and vice versa. When you have high prices and low renewables, other options may be relevant. Next chart, please, or next slide. Thank you. So if we look into the costs and the efficiencies of the technologies, if we start out at the left side of the slide, we can see district heating heat pumps. We can see tank thermal energy storage, and we can see pit thermal energy storage. So those are shown with their present and their future costs, and the future is 2050 as estimated by the Danish Energy Agency. And the maturity of the technologies is reflected in the expectations of the cost. So we see that heat pumps are deployed already, but there may be room for improvement cost-wise. Whereas the tank storages, you can imagine basically a silo with hot water in it. That is a quite mature and well-developed technology. And finally, the pit thermal storages are getting deployed increasingly, but still have room for improvement cost-wise. And please note also the quite relatively low cost of storing heat in this case, compared to many other technologies of energy storage. If we then look to the right of the slide, we can see the efficiencies. And if we start out looking at the heat pumps, so that is the one ranging from 350 to 700% presently, those spans are of course very, very large. And essentially what they do is that they apply electricity to extract heat from the surroundings to satisfy thermal demands. And the temperature of the surrounding energy sources can vary quite a lot. Also, your thermal demand, whatever that may be, can also vary quite a lot. So those are determining factors for the efficiencies. One example is that you may be able to extract an efficiency of 5.5 times of whatever energy you put in if you have industrial waste heat of somewhere between 20 and 30 degrees centigrade. So the differences are quite large, and generally there is an expectation of an increased efficiency into the future. Regarding the energy storages, we see quite low losses from the tanks. That is due to their quite short operational cycle that they operate in, and of course also the insulation. Whereas in the pit thermal energy storages, we have higher losses that tend to be more seasonally operated, so the heat can dissipate over longer periods. But then, as you're storing it at such a low cost, it still may make quite good economic sense for you. Next slide, please. Right. So on the technology readiness level and the deployment, as mentioned before, we have almost mature technology, or at least operating on the commercial scale in all cases. So heat pump and the different thermal storages. But as I said, there are room for improvement for heat pumps specifically, and the pit thermal energy storages. In the latter case, that has to do with the liner material, for instance, and the insulation of the what is essentially a big swimming pool with hot water in it. Then if we look at the deployment, the statistics on this are not so extensive as you would typically see for the electricity sector, but for heat pumps, in this case, we have a current deployment of around 1.5 gigawatts of capacity of heat on the European scale. And on the tank deployment in the Nordics, we have just below 100 gigawatt hours of capacity. And just in Denmark, we have roughly half of that in the pit thermal energy storage, which are very large storages. So there are quite few of them, but they have very high capacities. We can see that in the subsequent slides. So next slide, please. Here there is an example from Denmark where deployment of thermal energy storages, the large pit storages, is increasingly happening. The white ones are already deployed and operating, whereas the gray one in the western or the eastern part of Denmark is under construction. And as you can see on the sheer amount of megawatt hours, or we're actually in the gigawatt hour scale, these are very large capacities, enabling integration of large amounts of excess electricity. And I have a baby yelling in the background, so apologies if that is carrying through in the audio. Next slide, please. So on the future potentials, there are large uncertainties. Further studies are needed regarding this, but we also see quite large potentials. On the thermal storage side, one study has counted 750 gigawatt hours of thermal storage in Europe in total, where another study has just for the Nordics and the Baltics roughly almost twice that amount. So this illustrates the large uncertainty, but also the large potential that these may hold. On the power to heat side, one study at least shows quite wide deployment, increasing to roughly 24 gigawatts of electric capacity drawn from the grid from power to heat, mainly heat pumps in this case. So next slide, please. This final summary just goes to show that heating overall, or thermal energy demand, makes roughly 50% of the EU total demand. This is a significant share, but the amount of renewables as part of that is quite limited. So there are certainly some room for improvement in decarbonization, especially through sector coupling, integrating more renewables-based electricity into the heating sector. We have heat pumps providing coupling, as explained in my examples. The pit and tank thermal energy storages enabling to decoupling heat generation from the hour of demand or generation. And then finally, the cooling, which I haven't touched upon so much, but you can read more in the study, is showing very significant potentials also into the future, where cooling demands may increase. That's what is expected. Then next slide shows a few of the references. I unfortunately won't be able to join for the questions, but of course you're very welcome to get in touch in case you have any follow-up questions. And with that, I will leave the floor to Corin, which will present interesting material on the electromobility. So thank you.
Thank you, Daniel. Hello, colleagues. Just to very brief, we're running late, just to give you a very brief overview of the electromobility and implications on the entire energy system is where this where the focus of this presentation is. So if we start, this is just to give you a very quick picture about the penetration levels of electric vehicles in Europe. So you can see in here you can see on the x-axis is the years, and according to different studies, the International Energy Agency, McKinsey, and so forth, you can see that we expect to see about 20% by 2030 and maybe 40% by 2040 of electrification. Although these have now been significantly enhanced, there is now significantly more interest to try to, in fact, particularly in big cities, to have buses and taxis kind of running to be electric. So this is just to say that there is a very, very growing interest in the electrification of transport sector in order to achieve to meet the overall carbon target and also local emissions. We go to next one, please. This is the one of the core aspects of Working Group 1 is to understand the interaction of these vehicles and the system, and what are the integration challenges and opportunities to make that work. This is just to illustrate in here that you can see on the left-hand side, on the right-hand side, where the end consumers, you've got a kind of home-based charging, but there is now very significant interest and already demonstration using fast charging, and also you can see also at the bottom left, ultra fast charging. So there are now, in fact, charging stations are in also going to be developed, and there would be a number of them next year or two across Europe. There will be massive demonstration regarding these, also in addition to kind of home charging to big ultra fast charging, and that would also includes connection in terms of the electricity system, from kind of low voltage where the home is to kind of high voltage where the ultra fast charging would be, and then that's a close to kind of overall generation system. And what we have been in here looking into is this interaction between the charging and the entire energy system. So we go to the next one. One of the core challenges is associated with the impacts, and I'll show you that the peak demand would nearly double if we electrify transport sector and don't do it in a smart way. And there has been quite a lot of interest in here in terms of, you can see in the middle are the core topics: generation adequacy, transmission, cross-border distribution, address flexibility. And the question is, you know, if we electrify transport sector, as I say, you know, what is the implications on the how much generation capacity is required? You know, whether the transmission network will be able to accommodate vision vehicles, what would the implications on distribution grid and hosting capacity to be able to accommodate this local charging demand. And also there is also implications regarding flexibility on the generation side. You know, how are we able to quickly get on and off generators to be able to respond to how the charging might change. Go to the next one, please. This is just a very quick one to show you the what is the implication of the energy system at the high level. So you can see there are 3 bars. The first bar on the left is showing what is the energy increase if we electrify as planned the transport sector. You can see that if we electrify all vehicles, we have about 25% increase in energy consumption, electricity consumption. You can see the red one is that the peaks would double, which means you would need to, you know, if we do not do this in a smart way, we would need to dig all the roads and put the new, you know, cables in and double the amount of generation and so forth. And on the right hand side, in the diagram showing that if we've got a smart charging, which is possible because the flexibility of EVs is particularly the kind of domestic vehicles, private vehicles, is massive because the vehicles are stationary 90% of the time. So you could in fact charge them in a smart way, and there will be no implications or very little implications potentially on the, you know, on the infrastructure requirements. And also there is also opportunities of smart charging, but also vehicle to grid. And I will provide some information that's not all in our report, but this is just to give you also a feel of the background in terms of where these recommendations kind of come from, what the logic behind that is. So we go to the next one, please. This is just to, as mentioned already by colleagues, the flexibility is the core for facilitating cost-effective transition to low-carbon energy system, and the electric vehicles could potentially provide very, very significant resource of flexibility, both in terms of the smart charging, so that we use you know, the electricity in a proper way, but also this flexibility could also you know be vehicle to grid. We could potentially discharge vehicles occasionally for a small period of time without compromising service quality to support the system. You can see in here on this diagram, you can see the energy flows are from generation to demand, while this flexibility could provide flexibility to distribution, transmission, and generation system. And the whole system approach is one of the very important aspects that we should look at any of these you know, distribution or transmission or generation separately. That one of the core aspects is how we're gonna optimize the whole systems approach when making electric vehicles you know charged in proper way, so that there will be no compromise in service quality by the users. And that's one of the big challenges, but also a massive opportunity to make that work. And there is now significant amount of a demonstration project across Europe, and also commercial projects in terms of getting this vehicle to grid charging stations and so forth. We'll go to the next one, please. This is just to, there's a full second. This is the analysis which was carried out with, you know, with European projects regarding the implications of the deployment of electric vehicles, looking into, you can see on the right hand side, the kind of the national, international level, but also at the bottom is the kind of local distribution networks, low voltage. So and looking this in a coordinated fashion is what's important. And also the input data at the top, you can see kind of different penetration levels, and also the evolution of the system. And then this I'll show you just a quick result in terms of the how the European generation transmission distribution system needs to evolve, and what are the implications at the bottom. What is the impact of the rollout of electric vehicles on the European energy system? And just to give you the next one, please, just to give you a illustrative example, which is can I see the full slide? Anyway, it's something going here. I just say on the left-hand side, you can see what is the what are the emissions of electric vehicles per CO2 emissions per kilometer. And currently, it's red. It says that the emissions from new electric vehicles, cars in the EU, is about 120 grams per kilometer. You can see the electric in a business usual world would be kind of 20, say, call it 25. So it is significantly lower. But it's still if we don't charge them in a smart way, if we charge them during the peak conditions, then you would have a conventional generation with higher emissions. So they would be about, say, 25. But if we do this in a smart charging way, so that we charge, for example, vehicles, most of them overnight when they are not used, then you can see that the emissions reduced 5 times. So go to 5 grams of CO2 per kilometer. But if we provide vehicle to grid services, which is to do with if there is a frequency regulation, so you would potentially inject power for 10 minutes to the system, occasionally, you can see that the emissions are in fact negative, which fundamentally means that having vehicles on the system which are providing these flexibility services, the emissions are lower than if the vehicles were not there, but we are charging them. So this is just showing that at a high level that this is how critically important is a vehicle to grid and smart charging, because you would get massive benefits in terms of the decarbonization, which is one of the core points of the electrification of transport sector. In a way, we'll see in a minute, we're showing that the vehicles which provide vehicle to grid services should actually get paid for charging vehicles. So we go to next one. Just to give you a high level, can you just see the diagram, please, as well? Don't know what's going on. Yeah. So let us focus on this. This is again kind of how much euros per vehicle per year you should pay on average by charging your vehicle. You can see business as usual. It goes to kind of more than nearly 600 euros per year would cost you to kind of charge the vehicle. If it's charged on a smart way, it would reduce 6 times. But if it's providing vehicle to grid services, given that we are going to have very big challenges in terms of balancing renewables and also firm low carbon generation going forward, this is just showing that that you should actually get paid 885 euros for charging your vehicle, because you are reducing massively the cost of the system and also reducing the requirements for investment in renewable generation, because we've got this concept, so that we've got a fully integrated approach of the transport sector and the system. So we go to the next one. I know we are running out of time, but yeah. So this is just to illustrate there is a huge amount now of interest on these EV hubs, EV charging stations, and they are already now beginning to be deployed with potentially very large batteries or charging stations. So, for example, when you go to supermarket, there is now developments in a few places in Europe you know, when you for example drive electric vehicle and you go to supermarket, you can plug your car in, and which will be fully charged in half an hour by fast charging. So when you finish your purchasing supermarket, your car is fully charged. But also these systems could potentially also help significantly the support integration of the renewable low carbon generation, the system, and also just to kind of be a bit of extreme, you know, it was pointed out how important storage is. But if we electrify transport sector, there will be hundreds of gigawatts of batteries in vehicles. Can we make use of those, but rather than building, you know, other batteries as well? Can we make use of those batteries not only to properly, you know, drive the vehicles, but also provide the system support? And that is what this whole systems approach is critical in there. So if we just finish just briefly, because I've only 10 minutes, just to say that if you go to the next one, please. Maybe put the whole thing. Yeah, this is just to illustrate that, just to say that if these vehicles and charging stations could be used to support the system. This is just a diagram showing that if we do energy arbitrage, if we charge these batteries when we should, and also providing network support, also providing frequency and balancing system, and also capacity market, you can see that this is going to kind of, you know, very large values in terms of euros per kilowatt of the battery in the electric vehicles. So could be potentially very significant. This is an investment cost, so it's about divided by 10 to find out per year what the benefits would be. But this is just to say that this integrated approach to electrification of the transport sector and decarbonization of the power system is the core aspect to make that work. Thank you very much.
I don't know where Antonio went now. Antonio, are you there?
I did see him when I was talking, but
Yes.
now he disappeared.
Maybe take the next slide then.
Yes, actually, I see a question. Maybe while Antonio reconnects, I can already.
Antonio is back.
I'm here.
Oh, okay.
So I think next slide. Yes.
Thank you everybody for keeping the times in such varied and inspiring different subjects. So here we just draw some conclusions and some recommendations, also to start possible the question and answer session. So we need also a semantic definition, and this is by the way, European Commission is about to issue an important communication on what they call now smart sector integration. It was used to call it sector coupling. Even the name have to be harmonized, and this is now expected by the first week of July. So it's by definition an integration, an integrated approach. The main goals one is decarbonization, which can be cheaper or faster or broader than with other means. A very important point, advantage is the flexibility, which is provided on top of those who can come from demand response and only electrification. And what is important is the best use of infrastructures. That is either the existing one with operation stage or in planning. Planning is the most challenging because it requires coordination, which is already difficult now to forecast the load, the generation, which has become intermittent, and then the storage and the many devices. So it is an exponential growth of the variables to be optimized. Some of them are independent, some are interlinked. So there is a big need of advanced tools, but even metrics. How do we assess one project which is totally different from another one, from the benefit to the system point of view? The benefits come, the underlying rationale is to exploit the complementarities across the sectors, because you can have one sector infrastructure in one sector which are stressed in certain location and in certain periods and not in other one, and they can be complementary. The main sectors which we have seen to apply sector coupled projects are transport, heating, cooling, and some industrial processes. Power to gas is a bit special on this, because it is not only sector coupling, it's really a deep integration of multiple industrial processes. So not only typically hydrogen and synthetic fuels will help decarbonize sectors which cannot easily be decarbonized via electricity, but it opens also all the possibilities to optimize at the industrial level the fuels, if you have dual or multiple fuel options, and even an energy carrier for long distance, for example, crossing the seas and the oceans, probably convenient than electricity lines. So it is even competing with power lines. And then for long-term storage, molecules are typically near zero losses, because you have no leakage. Instead, for thermal, of course, you have the normal thermal losses on the long terms. In the next slide, I will leave the floor to Marie.
Thank you. Yes, so what we see is that there is a huge potential for electrification. Here it says that it could double the electricity consumption. I think in a Danish context, if we take the production of fuels for international travel into account, and we don't allow import of biomass, then we actually see that we might be up at around 4 times the potential, and or more than half, more than double, and actually 1/3 of the fuels we produce are then electrofuels. So that this is a huge potential we see, and what happens with these linking is that it can be a win-win situation, as Antonio was saying. So we can have the electrification help these difficult to decarbonize sectors, and these sectors can provide storage and flexible consumption for the power sector to really be able to integrate more variable renewable energy. So it can be a win-win, but it has to be managed smartly. So if we do this in a dumb way, as Goran was showing you, then it may just add the costs and we may have more greenhouse gas emissions, whereas if we do it smartly, we can reduce it. So we need to coordinate, and these different flexibility measures are in competition with each other. So as Antonio was saying, we need to coordinate this so we don't build double infrastructures everywhere, which would make this whole transition much too costly. So yeah, we can balance and stabilize grids, and if we do it dumbly, then we stress the grids and have too high investments. At the moment, we see that particularly the power to heating and cooling technologies are ready and commercial. Electric vehicles are fast coming up, and then when it comes to power to X, maybe we need a bit more scaling up and a bit more development for the technology to really be there, but we can start now, and we do have huge potentials even with the technologies that are ready today. Yes, I think one thing we could maybe also stress is that there has been talk of excess electricity coming from these variable renewable energy sources, and with all the different technologies we've showed you today where we can flexibly utilize electricity, I don't think there's any reason to believe that we will have excess electricity and negative prices going forward. I think we should believe that we have to build variable renewable energy capacity in order to service the demands in the other sectors, and there will be good use for the electricity and a lot of flexibility available. I think that was the conclusions, right? Oh, maybe I should mention that I forgot to say, when it comes to this deep coupling that you talked about with power to gas, some system analysis we do in Denmark, we see up to 1/4 or 1/5 of the district heating demand being covered by excess heat from these by refineries. So there is a good need to make sure that this is done in a smart way. And we can optimize, of course, the heat production at a national scale, but when it comes to gas and electricity, of course, it should flow across borders, and we need the international cooperation at an EU level. Thank you.
Thank you, Marie. I will add some recommendation, the last slide, and then we open to questions. First of all, I would like to stress what was clearly shown by Goran in the electric vehicle example. This is not a neutral thing. Electric vehicles either will be smart charged and they will benefit the system, or they will not be smart and they will stress the system. There is no business as usual. Either you have a problem or you have an opportunity, and the time to act is now, because this is the moment where charging stations are being developed and implemented. In general, all the project initiatives, well, sector coupling is a very differentiated hat for so many different initiatives. It is important to have also some metrics and methodologies to assess each project in case by case, using also maybe some harmonized assumption, but then it has to be very clear what is the use case and what is going to substitute and what are the clear benefits, including externalities, typically the CO2, but not only, and with a realistic duty cycle, because some of these in power to gas, for example, some of the steps are still in the laboratory level, and of course the conversion and other performance parameter has to be the ones of realistic duty cycle. If, like, when we test a car in the laboratory and then we test the performance when we drive from home to office, for example, is completely different. And also possibly extend this to the whole life cycle assessment, from raw material to disposal, which is something we should do actually in a general way. Just an example, and ENSO-E, the Association of Transmission System Operators in Europe, where I'm active, is making the typical tool, TUNDP, the Grid Development Plan, together with the gas association, the gas grid association, and also more stakeholders, evolving it into a multi-sector planning tool. This is something we definitely have to continue and implement by Europe for this. So now we are a bit late of time, but maybe we can also go beyond the 12 o'clock if there are no other limitations. This, Gustavo, you will tell us. Let's just open the floor to questions. And Gustavo, do you have some in the chats, or somebody wants to raise hand and just speak in a quick way a question, and we will try to reply?
Yep, absolutely. So I'm not sure if you can see the
thank you, by the way, for this
screen, but I can give the hand. I would give the floor, if he's still online, to Amjad Anbari. I can unmute you if you would like to present your question orally. If not, I can read it down. Yep.
Yes, I can hear you. Can you hear me?
Yeah.
Perfect. Hello, everybody, and thanks a lot for your informative presentation. It was really a nice topic. I'm Amjad from Aalborg University in Denmark, and I have a couple of questions for you. First of all is regarding the future challenges, especially in the in terms of the infrastructures that might be needed, and also other investment for this kind of cross-coupling. And the second questions would be about the business model, specifically for other vectors like the electricity system and district heating and cooling system, to motivate the end users or all other stakeholders to take part in such a kind of initiatives to make these kind of system integrations happen. So I would appreciate if you can comment a bit on this.
On the first question, the future challenges, actually, we hope we have given, even if a short time, a brief panorama, an outlook of how many and how different they are. I cannot list them, but at least the categories. First of all, in some of these set of carbon initiative, technology is well consolidated, in other it is not. So we need technology in terms of performance and especially costs, because as we said, all these projects are competing with other ways. We didn't invent something which didn't totally exist before. So we have to, especially to deploy it in large scale. And then there are so technical, economical challenges, and also I would say, so also going to the second question, we need to understand how to evaluate. Just a quick example, which is not even an innovation, is already existing. A battery, electrochemical battery connected to grid is definitely giving services to the grid. It is not still consolidated the way how to assess and then how to pay, because if we are going to private investment, we need to know what is the regulation. So regulation has a strong part on this, has to follow strictly, also with pilots, with demos, with sandboxes. And regulation means also business models. For example, also for charging electric vehicles, this will be a private business, not owned by grid operators. And it is important to see how the business models are profitable for a win-win-win situation for the operator, for the consumer, and for the grid operator/system. And then I would add also not only regulation and business model, but governance, because we are acting all of this in European policy, energy policy framework, the new Green Deal, which is setting targets in a top-down manner. But then most of the actions are intended to be bottom-up, so private investors and even consumers. So we have to match this, and we need an important and tight governance. Next question, please.
Can I add to this, Antonio?
Sure.
Just on the business models, I think an interesting example is from the Danish TSO that's looking into having dynamic tariffs and geographically kind of differentiated tariffs to motivate, for example, electrolyzers to be situated in places where it will benefit the grid and to operate in a way that benefits the grid, so that you don't play a flat tariff, but you do pay according to whether you service the grid or not. So this is an example of how you can work with it to make it feasible for these flexibility providers to really provide flexibility into, for example, the power grid.
Thanks a lot.
Thank you. You can take also the next question in place of Daniel, because you are also expert on subject.
Yes, I don't think that aquifer thermal energy storages was part of this study, but I think it might be mentioned in the white paper briefly. So I would recommend that you look into it, and also the very extensive annex that is to it. So that in the appendix there's a lot of more information. So please dive further into it and reach out to Daniel. I'm sure he'll be happy to answer more. And of course, I think in terms of the future challenges, what Antonio is also pointing at is that how do we coordinate this? How do we coordinate the development of the distribution grid and the transmission grids, both on the electricity and the gas side? Do we build new hydrogen grids to alleviate the pressure on the electricity grids? There's so much coordination that needs to happen, and at the moment, a lot of this is currently planned in silos. So we need to break down these silos and have these different planning agencies coordinate with each other, and this, I think, is a huge challenge.
Yeah, thanks a lot. I might just put forward my last question is about the ownership and the operating scheme for such a kind of integrated system. In this perspective, who would be the owner or who would be the coordinator to run the coupling facilities? Do you have any idea on this, or how the privacy would be preserved in such an integration?
I think this is part of what the next white paper will cover also, right, Antonio?
Yes, but we can anticipate that actually you touched upon this just 1 minute ago, Marie. And let's go by example. For example, storage and electric vehicle charging will belong to private actors, which can be existing market players or new ones. They will be connected to the grids, but the grid operator will not be either not owners and not operating, while of course being in charge, the grid operators, of the input for the external control of, for example, a battery charging and discharging cycles and possibilities. The problem here is, in general, to match the need of, in this example, the car owner and the need of the grid. Just to make a concrete example, I need to have a sort of contract with the car owner that he will guarantee that he will leave his car for 10 hours in nighttime available to me. I'm grid operator. And if he doesn't, he has to get a penalty. If he has a sudden need to use the car, he has to be penalized. Normally, grid operators are very prudent in this, and they apply a derating to all these when we talk about flexibility of load and demand response, but could be the same for electric vehicle charging. And in some cases I've seen in my country, derating up to 90%, because we are not sure, at least in the beginning, how much the car owner will actually, car owner, device owner, distributed resource owner in general, will apply to the, considering that for him this will be a very marginal part of the game. He need the car, he need the light, he need the heat, and if marginally we can pay him enough to do this, he has also to abide to the, and this requires not only coordination but also control, monitoring. And I would let a part in this answer the power to gas. This is a different animal to me. It's more industrial and has to be coordinated. Maybe it's easier for governance because it's a question of policy and big industries. So there are less number of actors, and but still a lot of interactions and the important vested interest. Just think, for example, all the gas infrastructure which tend to be stranded assets, as it is the case for many oil and gas companies, because not because the gas is finishing, but because there are restrictions on CO2, or for example in Netherlands there are problems of land subsidizing and earthquakes, so they cannot extract the gas which is there. So the gas is there, it's a stranded asset, and they are imagining to use at least the logistic pipeline storage, and then also maybe some final use like turbine with hydrogen instead of gas, which makes sense, but it has to be seen from all points of view. So the question you raised has no clear answer yet, but it's definitely on the top of the agenda.
Okay, I would give the floor to Heinz Wilkening if he can.
Okay, thank you very much. I'm Heinz Wilkening from the Joint Research Center of the European Commission, and I have one question. When you looked at the reforming or hydrogen generation, did you also look at thermochemical cycles or hybrid thermochemical cycles? because I imagine they can have higher efficiency rates. And the other thing is I was a little bit surprised about the very good numbers you have for vehicle for grid. I could think about that only by doing smart charging, you can almost reach the same thing with much less effort. If you think about that, your vehicle will increase in range, the battery will get bigger, and you don't have to charge your vehicle every day anymore. And yeah, one small question is, well, how much people will charge at Energy Hub, you think, and how much will they still charge at home?
Maria, I can take the part on electric vehicles, then I'll leave to you the steam reforming. Indeed, the numbers we've seen, they're a study in the UK, and I was also positively surprised of such a big positive difference from the point of view of the car owner. If you go to vehicle to grid instead of only smart charging, I think these studies need to be repeated also on local point of view. For example, a recent study in France by the distributor Enedis has showed that the most of the benefits are coming from passing from non-smart charging to smart charging, and going from smart charging to vehicle to grid adds only a small part of the benefits. So I think it is undoubtedly true that there are advantages both for the owners and for the system. The amount and the numbers have to be studied and fine-tuned by demonstration. I would say no more research, because every component is there. We need the demos. And the last question, if I understood, is what kind of charging will be there, because we have charging at home, charging at office or commercial building, and then we have charging on the parking and streets or parking places and highway. I would say these four main categories. This is I just give you an information that this has been deeply studied by a new partnership, 2.0 partnership, where ETIP SNET is deeply involved. We lead one of the 4 working groups, which is integration of vehicle into the grids, and this is we are writing the agenda. It will be a 7-year-long partnership with hundreds of partners from car manufacturers, battery manufacturers, grid operators, industry, and academia research centers. And this is which is kind of business model issue, is going to be in agenda there. Please, Marie.
Yes, I didn't. You were asking about steam reforming, and since we have been focusing on power 2x, so on the utilization of power in different sectors, we have been focusing on electrolysis. But we can say that a recent study from a Danish perspective sees that we are expecting lower costs of green hydrogen than blue hydrogen, i.e. hydrogen produced via steam reforming with carbon capture and storage. So we are expecting it can become competitive with that in the future. So I hope that covered your question. I was wondering whether Goran had a follow-up comment on the electric vehicles.
Yeah, just to say that, can you hear me, colleagues?
Yes.
Yes.
Yeah, just to say that one of the topics which needs to be, be a bit critical, hasn't been fully put on the agenda, is the alignment of the concepts of flexibility and also vehicles with the low carbon agenda, and that is something which is critically important. How do we get to this, say, zero carbon at the minimum costs? And there is a significant benefits in all of these aspects: power to gas and interaction between heat and electricity sector, but also electrification of transport sector, in terms of making us going to this low carbon world more cost effectively. And that's something which the policy and the framework would need to recognize. We've got now, there is a development in terms of, as Maria was saying, in terms of for example, charging mechanisms to have the equipment and the in the right places, which is very important. But also linking that with the low carbon agenda is what where I would suggest where the significant gaps are, because we can achieve, as we demonstrated, we can achieve the carbon target of building significantly less from low carbon generation, such as say nuclear and CCS and renewables, while meeting the carbon target. That is one of the important topics which is coming from this work.
And I will add on this that we give it for implicit, but it's better to sometimes explicit. All what we said are meaningful, not only if we have tight decarbonization goals, but also if we can rely on green electricity and on green gases. Otherwise, it's just a preparation for when delivering or vehicles. And then I use from carbon, from coal. The initiatives on iron are starting by definition with gray, with blue, if not even with gray. Because we don't have 100% gray. In the future, we will have a world by no electricity generation, and this will deploy long transition. Somebody from the audience, if this is not the case, it's also time to close the webinar. Thank you all the audience for the attention, for the questions. We have given the links to the references, and we will release the full presentation and recording in due time after adjusting some last-minute problem with the slides. And I remind you that June 30, there is the last of this series, which is about flexible generation, helping also on the sector coupling. And you find all the information on the ETIP SNET website. Thanks to all the speakers and to all the authors of the white paper. And a special thank to Zabala and Gustavo, who enacted the plan B. Luckily, we didn't have to go to plan C, but this proved to be effective anyway.
Good.
Bye-bye.
Thank you.
Thank you to all the attendees as well. Bye. Bye-bye.
Thank you, colleagues. Thank you. Bye-bye.
Bye.